So with all of that, I am very excited to introduce our next speaker and author of this amazing book. When I read this book, I just said, this is fun to read. Of course, it's full of great knowledge, but it's a really enjoyable read. It was really, really, really great. And I first came across him. I'm not sure how we actually got introduced, but he spoke at the meetup a number of years ago. It was one of our more popular talks. It was pretty awesome. And he says that the first language he ever fell in love with was R. So please welcome John to the stage. His music should be playing. There you go.
I can't believe I put that song. So is my audio on? I am live. This is happening. Okay. It is happening. Hello, world. How's it going? All right. So I assume you can also see my screen. I'm, oh, not yet. Okay, perfect. Good to know. Let me press this button that looks like a screen and then share the correct one. There we go. How about that? Jolly good. All right. So today's talk is a battle to the death between TensorFlow 2 and PyTorch. I can't wait to dig into all the content with you. And I'd also like to note that there are some beautiful illustrations in here from my book, Deep Learning Illustrated, which has this great sticker that I think everyone in the US has been sent one of these. Yeah, so Aglaé Bassins was the illustrator of Deep Learning Illustrated, and you will see a number of her illustrations in here from that book, as well as some that aren't even in the book. So for example, here's a beautiful illustration of my dog, Obo, who might be in the video at some point. So, whoa, what's that guy doing here? Now that must have been a very slow news day. Well, in January 2017, that beautifully coiffed news anchor provided me the opportunity to give an intro to deep learning at his Open Statistical Programming meetup in New York, as he just mentioned in the intro. And to give you a sense of how quickly the worlds of stats and machine learning change, only 3 years ago, that was the first lecture on deep learning at Jared's meetup, the first of what would turn out to, of course, be many. And at that talk, I met someone named Deborah Williams from the publisher Pearson, and since then, she's had me slaving away to create 40 hours of videos and dozens of online trainings on deep learning, culminating in the release of Deep Learning Illustrated in November of last year. Congratulations to the winner of that book, Mr. Foster, I believe it is. If you do come to the R conference next year, I will seriously give you a physical copy and sign it. I would love to do that for you. All right, so across all of the teaching that I now do on deep learning, a single question is asked more than all of the others combined. And that is, so TensorFlow or PyTorch? Given the popular demand of that question, I couldn't resist dedicating my lecture to the topic today. So first, a couple of slides on deep learning, in case you weren't already aware of kind of a high level what's important about it. So this guy is named Yann LeCun. He actually works in New York at 770 Broadway at the Facebook. He's the head of Facebook AI research, and he works there 4 days a week. And then 1 day a week, he lectures in the math department at New York University. Yoshua Bengio, he's up in Montreal. He teaches at the University of Montreal and has a startup called Element AI. And then Jeff Hinton, he's in Toronto, where he leads the Google Brain team and is a professor emeritus at the University of Toronto. These three gentlemen were awarded last year the Turing Prize, which is the equivalent of the Nobel Prize for computer science, for their work on deep learning. So we're going to, particularly in the interest of time, I'm going to focus on a landmark innovation by Jeff Hinton, by his lab. So in 2012, him and Alex Krzyzewski and Ilya Sutskever from his lab released this architecture that you now see on the left side of my slide. So this architecture is named after the first author on the paper, Alex Krzyzewski, so it's called AlexNet. And The key idea that I want you to get from this architecture is that it has many layers. So on the far left here, if you're inputting some input image, here we have an input image of a cat, then you have several layers of artificial neurons, which are they're designed to mimic in a loose way the way that biological brain cells work, so biological neurons. And these artificial neurons, through having several layers of them, they are allowed to have increasingly complex, increasingly abstract representations of whatever input data they're trying to map to an output. So there's actually some examples here along the bottom. So the first layer of AlexNet has 96 of these artificial neurons, and I've shown here what each of those 96 artificial neurons is specialized to detect. So in the first layer, you can see that each neuron is specialized to detect a straight line at a different orientation. And then the second layer can recombine those straight lines into curves and corners. So you see examples from the artificial neurons in that layer here. And then in the third layer, again, it recombines and allows more abstraction. And so as you get deeper and deeper and deeper, you get these increasingly complex, increasingly abstract visual representations until the model is able to make a very accurate guess as to what image has been put at the front. So if this was trained to distinguish cats from dogs, horses, and flowers, then when you input an image of a cat, you will get an output that says, hey, there's a 99% probability this is a cat, a 1%, a 1% chance it's a dog, a 0% chance it's a horse, and so on. So that's deep learning in a nutshell. And in 2012, when that AlexNet architecture was released, it made a huge splash. So Jeff Hinton and his team released that architecture into something called the ImageNet Large-Scale Visual Recognition Competition, which is still today the premier machine vision competition in the world. And you can see that in the first 3 years of the competition, all of the algorithms introduced were what I call traditional machine learning algorithms. So these could be regression, support vector machines, decision trees, basically any kind of machine learning that isn't deep learning. And whether traditional is a good name for it or not, don't worry about that. It's just so that I can distinguish it from what deep learning is. So all of the leading machine vision approaches were from these other realms of machine learning up until 2012, except for that one algorithm entry of AlexNet. And as you can see, it absolutely crushed all of the other competition. So year over year, there was no performance improvement in any of the other approaches. And so had not AlexNet been entered, you would have seen really no improvement year over year. But instead, there was a 30% improvement relative to the previous year's best model. And so everybody took notice. Academics, people working on commercial applications of machine learning, everyone started working on deep learning architectures. And by 2013, all of the top models were deep learning models, and it has been the case since. It's also worth noting that a team from Microsoft Research Asia got ahead of human accuracy in 2015. So that's kind of an interesting benchmark, the machines taking over. So in one slide, to summarize the main idea of the power of this deep learning approach is that with the other approaches, what I was calling the traditional machine learning approaches, whether these are regression, support vector machine, random forest, what have you, with those approaches, we typically spend the vast majority of our time becoming an expert in our data and extracting meaningful features out of the data. So writing functions to take in raw input images or raw video or raw sound and output what we think might lead to a meaningful signal. So the vast majority of our time, maybe 80 or 90% of our time as a traditional machine learning practitioner is spent extracting features from the data. And then we spend a minority of our time actually training the models. In deep learning, that is typically turned on its head, where we might spend little to none of our time engineering features out of the raw data, instead relying on our deep learning models to do that automatically, which is something they can do because of all these layers. So those layers can progressively and automatically extract increasingly abstract, increasingly complex features, allowing us to, as you can see from the preceding slide with the performance at the ILS-VRC, this approach of letting the machines automatically detect what the most important features are for predicting some outcome that we'd like it to learn to predict, that approach is more powerful than trying to do the feature extraction manually. So there are some limitations with deep learning, of course. Typically, we require, I mean, I'm speaking in broad strokes here, but typically we require larger data sets to make it work. We almost always require much more compute. And so it's because of those reasons that deep learning wasn't prominent until 2012. So up until 2012, a lot of these ideas, there have been a few theoretical advances in the last decade, but for the most part, the theory was in place. It was a matter of having the compute and the data storage to make deep learning rush ahead of traditional machine learning around that 2012 point. So since 2012, we've seen deep learning take over the world in millions of applications. So not just in machine vision, like you see here, the face recognition on your phone that allows it to automatically open. But by 2014, 2015, deep learning started spilling into natural language processing. So any device that does voice recognition is using deep learning to do that. Generative adversarial networks allow you to create really stunning fake artwork based on some particular inputs. So in this case, this generative adversarial network was trained on high definition celebrity photos. And these two people do not exist, but they sure look like real people. And then another big application area for deep learning is deep reinforcement learning, where, for example, in just a couple of years, machines have been able to overtake people at some very complex, intuitive games, such as the board game Go, thanks to deep reinforcement learning. So all of these topics I cover in detail in Deep Learning Illustrated if you're interested in learning more. For now, we need to actually move on to talking about TensorFlow and PyTorch. I'm already halfway through the talk in terms of time. So given how powerful and transformative deep learning is, hundreds of software libraries have sprung up in recent years to make designing, testing, and deploying deep learning models easy. So here are some of the most popular libraries today in terms of a Google search frequency. So TensorFlow, you can see for many years was the front runner. It used to compete with another library called Theano in 2016, 2017, but people don't work on Theano anymore. All of those people moved to Google to work on TensorFlow. And in those years, in 2016, 2017, there was this library Keras, which was designed as a high-level API to make building models initially in Theano, and then later in Theano and TensorFlow, and now primarily in TensorFlow, very easy. So the low-level TensorFlow is relatively complex, but Keras made it very easy. And as of the TensorFlow 2.0 release, which happened in late 2019, and I'll talk about that a bit more in the coming slides, Keras is a built-in module of TensorFlow 2, and it is the recommended way that the TensorFlow developers have for how you should build your neural networks. Now, there are a couple other libraries, MXNet, which is supported by Amazon and Blue, CNTK, the cognitive toolkit, which was supported by Microsoft. And as you can see, they're not nearly as popular, though maybe if I did this in Bing, CNTK would be a bit more popular than me doing this in Google. And so other than those, you can see that there's one other library that is eating into the share of TensorFlow and Keras, and that is PyTorch in green. So that is officially supported by Facebook, and it was initially being developed just by one gentleman at Facebook. And today we have a lot of people using both PyTorch and TensorFlow Keras. So in particular, looking at job postings from April of this year, you can see that TensorFlow has a modest lead over PyTorch in terms of being mentioned in job postings. However, across the United States, states in major urban areas, a sizable portion of job postings do mention PyTorch relative to the proportion that mention TensorFlow. So Seattle seems to be particularly a big lover of PyTorch, where 77% of job postings relative to TensorFlow mention PyTorch. And so across these metro areas, there's a 60% average. So in either case, both of these libraries are very prominent, definitely the two most important deep learning libraries. There's one other library that I didn't have in that Google search chart called Caffe, because it turns out people like coffee a lot more than they like deep learning libraries, so I can't really include that in a Google search. So obviously today we're primarily talking about PyTorch and TensorFlow, so I'll focus on those two columns here. A big difference between these two deep learning libraries was that for up until the TensorFlow 2.0 release in late 2019, late last year, TensorFlow had what's called a symbolic programming style, which is shared with Caffe. And this symbolic programming style was a little bit difficult to get used to. It was an unusual way of programming, and if I had time, I would show you examples of how that worked. But you essentially had to have at least this 3-step process in order to execute even very simple lines of code, like adding two variables to each other. Whereas with the imperative approach, you are able to, in the way that we've gotten used to in RStudio or Jupyter Notebooks today, just executing a line of code and having the addition or the multiplication or whatever mathematical operation we have in that line of code just imperatively execute in real time and produce a result. So one of the reasons why Torch so Torch actually really only works in Lua or C. However, so PyTorch is a complete rewrite of this Torch library for Python. And one of the big reasons why PyTorch became so popular in the last couple of years is because it was so much easier to use because of this imperative programming style. So this with TensorFlow 2.0, that was one of the big things that the folks working on TensorFlow were racing to do, was to get an imperative programming style in there as well. And so as you can see in here, TensorFlow is supported in lots of languages, including R, and I'm going to talk about that momentarily. It is primarily supported in Python and C, and it is officially supported in all of these other languages. The ones in brackets are unofficially supported, and I'll talk more about the R one on the next slide. So specifically digging into the differences between PyTorch and TensorFlow, you can, if you're familiar with Python, then you can think of PyTorch as being NumPy, but optimized for using on GPUs. And GPUs allow deep learning models to train typically much more quickly than you can by using CPUs only, so that's important. Both PyTorch and TensorFlow support GPUs, but PyTorch is a lot more just like that numerical Python package. So very, very easy to use if you're already familiar with NumPy. TensorFlow, on the other hand, was ported to Python from C++. So when you get, if you're used to Python, it's not Pythonic, really. It's kind of clunky to use. Lots of things happen in ways that you wouldn't expect. And that's because of this porting. And then when you get an error, you get these really long stack traces that typically don't make any sense. And so you need to just copy and paste whatever that error was into Google, and then you get a Stack Overflow result, and you copy and paste whatever that Stack Overflow solution was into your code. Whereas in NumPy, in PyTorch, because it was designed for Python, it's very easy to use. It behaves exactly as you'd expect. The stack traces are easy to understand and go along with. Now, for R specifically, there isn't an official PyTorch implementation. However, via the Reticulate Python interface, you can use the RTorch library. TensorFlow, on the other hand, has a well-supported interface that is created by the wonderful folks at RStudio, who also have a hexagonal sticker that was sent to you. So both of these libraries allow you to do what's called auto differentiation, which is a kind of partial derivative calculus that is critical for training machine learning models. And I have a slide coming up where I'll show you a quick example of that happening. And PyTorch allows this process to be dynamic. So you can very easily have data sets of all different kinds of sizes flowing into your model, and you can differentiate on those and train on those. In TensorFlow, up until the 2.0 release, and still today with the 2.0 release, if you're using Keras to build your models, you have a static graph, which means that you cannot have different sized data inputs. They need to all be consistent in terms of sizing. PyTorch has something called the Fast.ai API that allows you to build models very easily, I think too easily. I think that the Keras API that's offered in TensorFlow is a really nice middle ground if you're getting started in deep learning. Because of the short stack traces and because of how Pythonic it is, debugging is much easier in PyTorch. The advantage of TensorFlow is that it's much more widely adopted. In order to make PyTorch performant in production while also being imperative and easy to use in real time, there's something called the torch script just-in-time compilation scripts that allow you to deploy your PyTorch models into production efficiently. Whereas TensorFlow has many, in addition to those kinds of compilation scripts, it has many other kinds of support libraries for distributed training with TensorFlow serving, or deploying models into someone's browser in JavaScript, into embedded devices or phones with TensorFlow Lite, and the TF-Data and TF-IO libraries allow you to very easily have all of your pre-processing happen inside of a TensorFlow model. So overall, PyTorch is more enjoyable for model design. TensorFlow is better for production deployments. I'm going to have to skim over these slides, but I just wanted to give you a sense of what it's like doing various operations in PyTorch versus TensorFlow. So here we are creating a simple vector tensor. As you can see, things just kind of look nicer and cleaner in PyTorch relative to TensorFlow, but you get a bit more information in TensorFlow. You can see more information in this Jupyter notebook. I am out of time, so I'll just quickly rush through these final slides. For the automatic differentiation that I described a couple slides ago, so for example, if you wanted to find, if you take the derivative of y equals x squared, and then you plug in the number 5 for x, you'll find that the derivative of y with respect to x at x equals 5 is equal to 10. And so to calculate that with automatic differentiation in PyTorch and TensorFlow, it's easy in either library, but it's definitely easier in PyTorch. You have these weird with statements in TensorFlow to make it happen. And in terms of creating a model, it's about exactly as easy in PyTorch versus TensorFlow Keras. In terms of training a model, it is way easier in TensorFlow Keras in the Keras module than it is in PyTorch. But if you like having control, or if you're a little bit more experienced with deep learning, or if you'd like to have dynamic input sizes, then you'll definitely want to be using PyTorch instead of the TensorFlow Keras way of doing it in a single line. So in conclusion, TensorFlow or PyTorch? Well, the answer is both. So if you understand one, it's easy to understand the other. If you're using deep learning professionally, you'll run into both all the time anyway, as we saw from those job description stats. There's a more granular perspective on model training in PyTorch, which makes it a little more complex than Keras, but ultimately PyTorch is more flexible than Keras. PyTorch is more fun and easier to debug because the stack traces are straightforward. TensorFlow, in contrast, has a stronger open source ecosystem for distributed training and more flexible model deployment options. So if you're brand new to deep learning, I'd recommend starting with the TensorFlow 2 Keras module, then moving to PyTorch once you're comfortable with it. For example, by working through my book, Deep Learning Illustrated, in which we do exactly that. And also, you can use the Onyx Open Neural Network Exchange library to transfer between TensorFlow and PyTorch seamlessly. So you could use PyTorch for that fun interactive model development, and then when you're ready for your beefy deployment, distributed training, or deployment into various kinds of systems like JavaScript, browsers, and so on, then you can translate your model from PyTorch into TensorFlow to do that. So yeah, if you're new to deep learning, I definitely recommend the process that I just followed on the last slide. There is as a conference attendee, you get a deep discount on any data science books offered by Pearson. So 40% off, 70% off videos. Check out that link and this checkout code to get those discounts. And yeah, please do stay in touch. Thank you very much for being here. Would love to have met you in person. Consider signing up for my email newsletter. I push out lots of free videos on machine learning foundations, and deep learning, as you saw examples from on the preceding slides. Connect on LinkedIn, mention that you were in today's talk. I'd love to be able to kind of put a name to an experience and a face to an experience and follow along with your career, particularly if you're in New York. There's a good chance we'll see each other soon anyway. As I mentioned, I post lots of videos on YouTube, and I tweet some stuff as well. And I've got a podcast, the Artificial Neural Network News Network, where you can stay up to date on the latest in machine learning news. All right. I'm all done. Thank you very much for your attention, and I look forward to meeting you in the future and answering your questions.
Thank you very much, John. Just a quick note, I noticed you mentioned R-torch via Articulate. There are rumors abound that there's going to be native torch bindings in R without going through Articulate. So that's going to be a lot of fun when that officially comes out. Another tradition we have at this conference is we usually start putting up Bloody Marys around 8 a.m. So if anyone has a beer, now's a good time to drink one.